Hi students, now we will discuss about that torque and having relationship with the magnetic dipole moment acting on the current carrying loop. Actually, you may have seen such type of arrangement in a AC generator. So yes, we this figure we will use an AC generator as well. But first of all, let's say you have such type of current carrying loop. Let's say current is going inside and as per it is rotating, the direction of a magnetic field and magnetic dipole moment is been shown in front of you. You can also say that these are the two magnets. Let's say I'm just mentioning that it is a north pole of a magnet and south pole of magnet. So you can just assume that the current is passing like that. The magnetic field is like in this direction. So my fingers are indicating direction of magnetic field. So first of all, you can just learn is that whenever such type of circular loops are there, when current is in a clockwise direction, it is behaving as a south pole, and when my current is moving in the anti-clockwise direction, it is behaving as a north pole of magnet. So you can just see that my current is moving in the clockwise direction, so this much point is behaving as a south pole and this is also behaving as already south pole. So both are having repulsive nature. Same is the course for the north pole, and this is behaving as a south pole, so it is having attractive type of nature. So at this point and at this point we will just experience force. So let's say this is the coil. If you are just viewing from the front point of view, let's say this is the coil. Let's say from the front view it will look like a straight line to you, but whenever I'm just tilting it, then you can just say that it's some thickness or like that. Same is the course over here. It's having that a length is called as a small a, and I am using that notation for my formula. So first of all, I am just using that my width for this much segment is called as a, it's a width is called as a length, and that is called as a width and length, both are a and b. I have area is called as a ab, so I'm just saying that area of coil is called as a capital A multiplication of AB. So I'm using it, and there are two methods to prove this expression. So force by the first part and force by the second part. You can just say that I have just mentioned that F1 and F2 over here, so it would be quite clear for you. So this is a F1, this is the line, entirely it is A, this is the midpoint or axis, and this is a by 2 and a by 2. So this is the entire part A. So force F1 is downward and force F2 is upward, so both are following Newton's third law. So I can have a F is equals to, as per our formula of F equals to BIL that we have already proved. So I have formula that is called as a F equals to F1 equals to, from that B segment, BIB. Same is the course for my F2, that is also called as a BIB, but this is in the opposite direction. So I have just mentioned that F and F, that is called as a, this is the formula. Now I want to utilize my torque notation. So you are aware about that expression, that is called as a torque equals to, torque equals to R cross F, and it is also having the sum of the different T1 and tau 1 and tau 2, as R is called as a perpendicular distance and F is called as a force. So I can just use this part, total net tau when my theta both are perpendicular, it is called as a pi by 2. You can see that this is the perpendicular distance I have, a by 2, and my force is in a opposite direction, so both are perpendicular to each other. So I can just say that that is called as a, first of all, my area perpendicular distance, perpendicular distance is a by 2 and my force is F1. Same is the course that my perpendicular distance is a2 and that is called as a, now I am just saying that F1 and F2 both are equal. So from equation number 1 and 2, I can just say that my tau is equals to uh, a by 2, that is called as a b ib of twice times. So I can just say that a tau is equals to, I have ab and ib, and you are aware that my area is called as a ab. So my formula is called as a tau is equals to bi and a. I have mentioned that only for the one loop, and if for n number of loops, my formula will become tau is equals to bina. Mind well, this is the capital N I have placed. I haven't placed a small n because small n cannot be possible over here. So I have mentioned that capital N. So you can say that my formula of a torque equals to BIA, or if number of loops are there, it means that I have just taken only one coil. Instead of this coil, I have n number of coils. Capital N would be of axis, like it will look like a wheel with some patches. So my formula will be called as a tau equals to bina. But now, right now, I want to utilize another formula and want to show that expression is also dealing with our force part. So another method I want to just show indicating this formula for you. Let's say in this figure you can see that previously my magnetic dipole moment was over here. Because why I am using this word magnetic dipole moment, you are aware about electric dipole moments properties. You are aware that both are applying of equal value in opposite direction. Same is the course over here. We have two poles, both are of the same value, are located at the same distance. So I can discuss about magnetic dipole moment by experimenting our external force. This has been line, red line, which is indicating another position of my force. So it is indicating previously my magnetic dipole moment was existing over here. After application of a theta, it has been received over here. So that is called as inclination in the direction. So I am just again using that tau is equals to RF sin theta. So I can have tau is equals to tau 1 plus tau 2. So I can have tau is equals to my perpendicular distance is a by 2, and that is called as f sin theta, and same is the course for a by 2 f sin theta. You are aware that f1 and f2 both are equal. So I have mentioned that f1 and f2 both are f. So my value of tau is equals to af sin theta. But you are aware that f1 and f2 both contains the same value bib. So I am just mentioning that from 1 and 2 I can have a tau is equals to a small b I and b sin theta. So I can have a tau is equals to, that is called as ai and b sin theta. But you are aware that that is called as the area AB, and my magnetic dipole moment is called as M is equals to IA. So A and I is there. So I can have a torque tau is equals to MB sin theta, or you can just place this formula as in the terms of a vector, that is called as M cross B. So this is the formula which is giving me a reminder of a comparison part which I have just used in the first chapter, that is called as a P cross E. So tau equals to P cross E and tau equals to M cross B. This is for the electric and this one is for the magnetic. And this one is quite simple for you, that you can see that my theta, when my theta is maximum, it means pi by 2, my torque is maximum. So if I am putting that theta equals to pi by 2, at that time my torque is maximum. When theta is equals to 0, my torque is minimum, it will be 0. So this is the relationship between the my current carrying conductor which is applying torque on such type of a loop. So I have found it out relationship of a torque, and another relationship is dealing with the magnetic dipole moment and torque. So after that, by using this formula, we will just discuss about application of this formula. From this formula we will derive that equation of voltmeter sensitivity or ammeter sensitivity, or how our normal domestic electric meters are working. So keep in mind this formula, it is quite easy for you to memorize.